Example 7.4. A 3 meters long ladder weighing 20 kg leans on a frictionless wall. Its feet rest on the floor 1 meter from the wall as shown in the figure 7.14. Find the reaction forces of the wall and the floor. Okay, as shown in the figure, a 3 meters long ladder weighing 20 kg leans on a frictionless wall. Its feet rest on the floor 1 meter from the wall as shown in the figure. Find the reaction forces of the wall and the floor. Okay, according to the question, here there is a ladder. Sorry, it is wall. Okay, so this is wall. Then a 3 meters length of ladder is lean like this. Okay, this is our ladder. Okay, its length is given, that is 3 meters, and the foot of this ladder, it is about a distance that is 1 meter from the wall. So let us see some. For suppose this is A and it is our B. That is AB is our ladder, and the wall uh, from the ladder to wall it is C. Okay, sorry. Wall is C and ladder is A. From that distance is 1 meter. Okay, then according to the question, so here we have to find out that find the reaction forces of the wall and the floor. Reaction forces by the wall and by the floor. Okay, so when this ladder is placing like this ladder is applying a force on the wall in this direction. This is F, action force, and this wall is applying a force on the ladder in opposite to the direction of action, that is reaction forces. Okay, this is the first one, F1, reaction force. Okay, so then another one, the weight of the ladder, it is acting at the middle of the uh, wall, always downward, that is W. And then one more force, so this ladder is applying a force in this direction. Ladder is applying a force on the surface, means here that is how much. For suppose it is F, it is action by the this end of the ladder, and the reaction force applied by the floor, not surface, it is floor. Okay, the floor is applying a force in this direction. This is here we called F2. Okay, so this F2 is reaction force. It is reaction force by the floor on the ladder. Then this reaction force is not a direct vector, so it is like this. Okay, this is F2. This force we are resolving into two components. Okay, one component is along in this direction. This is called a frictional force, and perpendicular to that another force, that is normal reaction by the floor. This is our normal reaction N, and this is our frictional force, and resultant of these two forces is nothing but reaction force by the wall. Reaction force by the wall. Now we have to find out this F2 and this F1. Okay, so for suppose this ladder, if ladder is in translational equilibrium, translational equilibrium, So translational equilibrium means there is no translational motion. Means translation means it is maybe moving along the x-axis, that may be positive or maybe negative, or maybe upward or maybe downward, that is along y-axis. Okay, so what are the forces are acting in the direction of x and in the direction of y? So if we are observing that, so there are some forces are acting along x-axis and some forces are acting along y-axis. So y-axis I am taking here vertical direction and the x-axis I am taking here horizontal direction. Okay, if ladder is in horizontal horizontally horizontally equilibrium horizontally equilibrium, sum of the all forces in horizontal direction equal to 0. Sum of the all forces means all the forces along the x-axis is equal to 0. So along the x-axis, what are the forces are there? One is reaction force, which is not required here. Okay, for understanding only we are mentioning this is okay. This is not required. So the one force is F1. It is reaction force by the wall. It is negative x-axis. And another force here, it is frictional force. It is acting towards positive x-axis. So we can write some of the forces, that is frictional force, it is positive, so I am writing a Fr, and this is reaction force, it is negative, that's why F1 is equal to 0. So from that we can write it is, that is F1 is equal to Fr. Okay, so if ladder is in vertically equilibrium, so sum of the all forces along y-axis equal to 0. Sum of all forces along y-axis equal to 0. What are the forces are acting along y-axis? Okay, one is the normal reaction, it is upward direction, and W, it is acting downward direction. Okay, so write down here, that is normal reaction, it is acting upward positive, and W, it is acting downward, so it is negative, so W is equal to 0, and it is equal to, that is N is equal to W, and that is equal to W is equal to M into G. Okay, so that is N or W is equal to M. M is equal to mass of the ladder. Mass of the ladder is given, that is 20 kg, and G is equal to 9.8, and it is equal to 1.10 cancel, and this is equal to 196 newtons. This is the N or W. Okay, so then if this ladder is in rotationally equilibrium, if ladder is in rotational rotational equilibrium, then sum of the all torques equal to 0. Rotational equilibrium about A, point A, means this point A is behaves like a what origin. Okay, so this our ladder is rotationally equilibrium about A, means A is acting as a origin. Then about that origin, our ladder, this is our ladder, black one, so this is our ladder, and it is rotating about like this. Okay, maybe clockwise or anti-clockwise, we have to choose one direction. Okay, means this A is behaves like a origin, from that origin ladder is rotating. Okay, so but here we are talking rotationally equilibrium. If it is rotationally equilibrium, sum of the torques equal to 0. So if sum of the torques is equal to 0 about A, then we have to apply here torque. So we all know that torque tau is equal to R cross F. Okay, if these two are in 90 degrees. Okay, this is 1 meter and this is ladder is 3 meters. By using Pythagoras law, then it is equal to, we are getting, this is 2 root 2 meters. Okay, so now it is our ladder, this is our ladder. Okay, and one end of the ladder, one force is acting, this force is how much? F1. Okay, so means here, um, this is the perpendicular distance and this is the force. Okay, R is the perpendicular distance and force, then the force is acting in this direction. Okay, so means this is R and it is our force. Okay, so open your fingers along the first vector and mold towards the second vector, then it is out from the plane. So that's why it is positive torque. So then write down here the positive torque, distance and force. Distance is 2 root 2 meters and force is F1. This is distance and it is force. Okay, R F, it is outward, so that's why it is positive. Then one more also is there, it is our origin. Okay, now it is our ladder and here there is one more force is acting, that is W. It is acting downward, so that's why it is acting at middle of the ladder, so that's why it is exactly at middle point from this distance. This total distance AC is 1 meter, then half of the, that middle of the this AC is nothing but half meter. Okay, so now here this ladder is experiencing this force and it is about a distance here half meter, so that's why the perpendicular distance is here, that is half meter. Okay, and the force is here W. So then the torque, so means here it is like this our ladder and this force is acting here. Okay, then it is our perpendicular distance. So perpendicular distance is of perpendicular distance is of 1 by 2 and the force here, that is equal to W. And is it negative or positive? Okay, look at this. Okay, this is the what? R, half meter, it is in this direction, this is R and force is acting downward, so this is R and it is downward, so it is into the plane. Once again look at this distance from AC to a middle of the this distance, that is AC, this is R direction, then the force is acting downward, pulled towards down, then it is into the plane, so that's why this is negative, is equal to 0. Okay, sum of the all torques about A is equal to 0. So this is root 2, this ladder here, this ladder is acting a force F1 on the ladder and this is the perpendicular distance. Then here this is the perpendicular distance and here the force is acting W. So here it is positive torque and this is negative torque, so sum of the torque is equal to 0. Then from this we can write, that is 2 root 2 F1 is equal to, this is uh, half into W and that is equal to half into W is equal to, already we got here, that is equal to 196 newtons. Okay, so then that 196 newtons, if we are dividing that, so from this 2 1 ja 2 9 98. Okay, so that is 2 root 2 F1 is equal to 98 newtons. Okay, so from that F1 is equal to 98 by 2 root 2 and this is equal to, that is 34.6 newtons. So this F1 is how much? This is the first reaction force. It is the reaction force. F1 is equal to 34 newtons, and which is also equal to the frictional force. F1 is equal to frictional force. So that's why F1 is equal to Fr is equal to 34.6 newtons. So one reaction force is completed. Then we have to uh, calculate the another reaction force of F2. Okay, so here this is the our F2. Okay, this F2 from this, if we are this normal reaction we are shifted to here, this is our N, and it is a right angle triangle. So in this right angle triangle we want to this F2. Okay, so this F2 is the hypotenuse and these are the two sides. So according to the Pythagoras law, F2 is equal to under the root of N square plus Fr square. Okay, so N is equal to, what is the N is equal to? N is equal to, this is 196 whole square plus Fr square. Fr square is equal to 34.6 whole square. Then it is equal to, after solving this, we got that is 199 point 199 point is 199 newtons. Okay, this is the second reaction force. Okay, these are the reaction forces. But in the book they are mentioning what is the force F2 makes an angle alpha with the horizontal. So this ladder is making some angle, not ladder. This force is acting. Sorry, um, make some angle with the floor. So that is, very well. This is the theta, and here this is opposite side, and this is our adjacent side. So from that we can find out the tan alpha is equal to opposite side. It is our nothing but normal reaction. Okay, that is N by Fr. Fr that is equal to maybe we got it is 4 root 2. Okay, and that is alpha is equal to we got tan inverse of how much? 4 root 2, and that is equal to 80 degrees, which is not required, but this reaction force by the floor. Okay, this is reaction force by the wall. This is our example 7.4.